So in this lecture, we're going to talk about section-active long spans. In other words, long spans that take beam principles, bending, moment diagrams, cross-section, section modulus, and sort of either hack them or blow those up to the sort of scale that we're used to talking about when we talk about long spans. I'm going to start with this image, which if you look closely, it's the Kimball Art Museum in Fort Worth by Lou Kahn. You may think, well, wait a minute, this looks like a vault. Isn't that a form-active structure? And by the end of this lecture, what I want you to be able to recognize is that while this looks architecturally like a vault, it has all the characteristics of a section-active long span, in particular something that we'll call a long vault, which is a variant of a folded plate. If that seems confusing, we'll sort of work our way up to it. You won't be the only one who has to think through why this particular structure is a long vault or a section-active structure instead of a form-active one. Kahn himself was confused about this. Hopefully by the end of this suite of lectures, you'll agree with me and you'll be able to explain it yourself. We'll go through three topics. This first little bit, we'll talk about what I think of as hacks, where we take standard beams and do things to them that make them much more efficient and therefore able to span farther. We'll talk in particular about a kind of beam originally called a fish belly beam, but what we can also think of as a moment-sensitive beam, in other words, looking at shaping the beam in the longitudinal direction. And we'll also look at what are called castellated beams, which are beams where there's fabrication done typically to a steel W shape that turns it into a much more efficient use of its material. And then in subsequent videos, we'll go into folded plates, a form of section-active structure where we kind of trick a thin plate, usually out of concrete, into thinking that it's a very, very deep beam. And then we'll look at long vaults. In other words, these Kimball-like shapes that, even though they look like they should be spanning in the short direction, are actually engineered to span in the long direction, and what that means both structurally and architecturally. So we'll start with basic beam theory and how we can kind of blow that up to long span scale. If we go back to 347, a class where we were talking a lot about individual structural elements, beams, columns, foundations, there was a moment where we were looking at moment diagrams. In particular, how we draw through a sort of thought exercise where we think about the load that's on a beam, the way that beam is supported, and the resulting distribution of both shear and moment throughout them. You may remember that we talked about things like the slope of the moment diagram is always equal to the value of the shear diagram, things like this. What I want to focus on right now, though, is literally just the shapes of these diagrams. If you think about the moment diagram for a beam, what it's doing is it's telling you where the greatest moment is. And so, for example, in a simply loaded beam with a load right at the center, simple supports on either side, we get this very simple shear diagram where the reaction pushes it up, the load pushes it down, the reaction pushes it back up. And what that tells us is that we have a positive slope going to an inflection point where the shear diagram crosses zero, and then a negative slope. And if you think it through, that's just a simple triangular shape. The moment is at its greatest at the point of load, and it's at its least on either end. So we can design any number of beams for that. And we went through and we looked at how we would select a steel beam. You might remember we looked at the section modulus, which is a measure not just of depth, but where the cross-sectional area of that shape is relative to the neutral axis. And then we sized the beam based on the section modulus that we thought we would need. If you look at the moment diagram, though, you realize that we're going to be giving up a lot of weight if we simply select a regular steel beam, a regular W shape, because we don't need as much depth or we don't need as much area. We don't need as much section modulus if you want to be really accurate about it. At the ends, as we do in the middle. The middle is where we need the greatest depth, the greatest amount of material farthest away from the neutral axis. And so ideally, we would like to design a triangular beam for that situation. Now, in fact, in the early days of iron construction, we saw exactly this. We saw engineers and builders coming up with what they called fish belly beams. This is a classic example right here in the middle. Because they were using cast iron, they could mold whatever shape they wanted, and they knew to make the beam thicker in the middle and thinner at the ends. Can't be infinitely thin because it has to take the shear, the load of the beam, and resisting its tendency to shear off at the supports. But you can see that A and B in particular have got this kind of fish belly shape, putting the greatest depth of the beam where you have the maximum moment. And you may remember that we briefly looked at this very curious beam from Charing Cross Hospital in 1830, where they actually not only made a fish belly beam, but they actually tuned the material to what they thought was going to go, the stresses that they thought were going to be in the beam. So the top bit here is made of cast iron, which is easy to shape into a variety of geometries. So you can see that they've got a kind of good moment diagram shape, a good longitudinal shape. And then interestingly enough, they make the bottom out of a rod of wrought iron, which is much stronger in tension than cast iron. So they knew that there was compression at the top, tension at the bottom, just like in any beam we would design today. Well, what I want to focus on for the moment is that fish belly shape, knowing that if you want to fine-tune a beam longitudinally, you can save weight by making the beam deeper in the middle and thinner at the ends, right? Tuning the longitudinal shape to the actual moment stresses that are within the beam itself. Now, today we don't often see this in steel because we typically roll steel, and we can't get the kind of sectional variation that you could if you were casting every beam. It's much cheaper to roll steel. Steel is a much better material for structural design than cast iron. So we live with that. We live with the fact that in the longitudinal direction, there will be some lazy material at the ends where we don't have as much bending moment, and we really don't need as much depth. We really don't need as much section modulus. Nevertheless, it costs too much money to change the longitudinal shape of a steel beam in particular. Where we do see this principle coming back, though, is in concrete. As we get better and better ways of fabricating concrete, or more kind of nuanced or responsive ways of forming it, we have started to see these fish belly shapes come back. And here in particular, the Stereoform slab project by SOM Chicago in 2019. You can see down here, this is the formwork. They had all of this styrofoam formwork custom cut using 3D printing technology. And they did that so that they could get this very, very pure structural shape. In this case, these are moment connections at the columns. So the slab has to be quite deep there because that's actually where the greatest moment will be. And then you can see that it bulges out again in the middle where they calculated that the second greatest moment would be in what we would call a continuous beam or a continuous slab. And they're able to fine-tune the longitudinal shape of the girders supporting that slab to where they know the greatest moment is going to be. Right? The same principle at work in 1820s, 1830s iron construction, here applied to concrete technology. And the savings in this one beam may not be very great, but you could imagine that this would be a way to save a lot of material if you were doing a multi-story building. Right? If there are 30 or 40 of these, the weight of all that concrete that you're not using starts to add up, right? The savings start to add up. So in the longitudinal direction, we have ways of hacking the beam shape to save weight, to allow ourselves to use that weight either to span a longer distance or to put more load onto the beam. It's pretty effective. We can make generally like more efficient beams and girders out of it, but it's not going to get us maybe to long span dimensions quite. The other thing we can do, though, is that we can turn and we can look at the cross-section of the beam. And we've already done this a little bit. We looked at the difference between a rectangular beam of solid section, which is consistently dimensioned all the way across or all the way up and down its cross-section, and we said, hey, look, if the section modulus theory is right, then anything we can do to concentrate that cross-sectional area at the extreme edges of the beam, remember the technical term extreme fibers, will get more and more efficient because we'll be using the material only where it's the most effective. And remember the logic behind an I-beam or a W shape is that we're putting most of the beam's material at the top and bottom in what we call the flanges. That's where the beam is going to work the hardest, basically, to resist the combined tension and compression that comes with bending. So a W shape is already kind of hacked. We still need a web there to hold those two flanges apart from one another to make sure that they work in conjunction with one another, but we're minimizing the thickness of the web, and therefore we're concentrating the dead weight of the material, also the expensive material. We buy steel by the pound, so we want it to be working as hard as it can be. We're concentrating that where it's going to work the hardest. Now, we can combine the two. We can take the idea of a W shape, we can combine it with a fish belly principle, maybe cast. We can do things to the web that minimize the amount of material there. And if we're willing to spend more and more on fabrication, more and more on assembly on site, we can get very, very efficient shapes. So here is like a fish belly truss beam, where we've actually taken not only the dead weight of the longitudinally lazy material out. Notice it's much thicker in the middle, where it needs to work harder, much thinner at the ends where the bending moment isn't quite as great. We can turn that into a W shape. You can see that you can think of this as a compression flange along the top and a tension flange along the base. And we can start to take material out of the web, right? Material that's closest to the neutral axis. If we take that away, and we leave just enough web to make sure that those two flanges work in conjunction with one another, what we find is we have a very, very efficient beam shape, right? Efficient beam geometry. A shape like this is going to cost a lot more than a typical W shape, just like a W shape costs a little bit more to fabricate than a rectangular section. But look at all the material that we're saving. If you look at the solid section versus the kind of hacked together shape, what you see is that we don't have as much material, and therefore the beam doesn't have to carry as much of itself over the span. Remember when we were doing beam design, we kept having to go back and throw the dead weight of the beam into the equation, and very often that meant that the beam couldn't actually carry the load that we wanted it to over the distance. In the extreme case, you could get a beam so long that it couldn't carry its own dead weight. And what we're doing here is we're finding ways basically not to make the beam necessarily stronger, but to make it lighter, to take away weight that we can then use either for live load, or we can actually use it to extend the beam's working length, the workable length that it can span on its own. So remember too, this diagram, I'm sure some of you are going to break out in hives to see all this again, but I'm showing this again just to show that the other principle, if we look at the beam in cross-section instead of longitudinally, is to remind ourselves that this line here, the neutral axis at more or less the centroid of the beam shape, determines basically where the beam is going to have no tension, no compression. In other words, there's no reason to have any material there because it's not going to be able to resist the bending load that we're putting on the beam. The further we get from the neutral axis, the greater the stress is going to be in each one of those fibers or infinitely small little bits of material. And so if we can put all of the material at the extreme edges, right, to resist what's usually the compression stress across the top, what's usually tensile stress across the bottom, taking all of those little tiny infinitesimal areas and concentrating them at the beam edges, the beam is going to be more efficient. So the cross-sectional strategy that we have, if you think about it, the longitudinal strategy is don't put material at the ends of the beam where you don't need quite as much resistance to bending moment. The cross-sectional strategy is don't put much material around the neutral axis. Do what you can to remove that lazy material around the centroid of the beam. So how do we do that? How do we take the lazy material out of a W shape? We could certainly come in and with plasma cutters, we could sort of take out whatever shapes we want, but we have a fabricational trick we can use called castellation that helps us do this really efficiently. And what we do when we castellate a beam is we slice a cut through the web that has a regular repeating shape to it. We then separate these two cut halves of the beam. We shift them 1/2 of a cycle, and you can see that we go from a beam that is this depth to a beam with exactly the same weight, exactly the same amount of steel that is now a little bit larger. And then it has these giant openings that are, you'll notice, centered right around the neutral axis. We come back in and we weld those pieces together. Here we're welding the hexagonal tabs. So if you think about it, that piece of the beam before we cut it was sitting right there. We've sliced this hexagonal like zigzag shape through it. We've shifted the beam a little bit, and now all of a sudden we get basically free depth. And remember, depth is key. The section modulus of a beam, the measure of its efficacy in bending, is inches cubed. Inches squared is area, and the third factor is one of just pure length. So remember, in section modulus, we're measuring not just the overall area, but we're multiplying each one of those little areas times its moment arm around the neutral axis. So if you look at what we've done with the castellated beam, we've actually taken a W shape that is, say, maybe like 6 inches deep, and now we've made it maybe 8 inches deep. And we've taken the webs and we've literally just given them that extra moment arm. And it's cost us nothing in terms of material. It has cost us something in terms of fabrication, but we can, of course, set this up on a plasma cutter. We can do robot welding. We can do this relatively easily. And now we have really a hacked beam. We have what had been a 6-inch W shape, and now we have an 8-inch W shape. It has a higher section modulus because the flanges are further from the neutral axis, but it has exactly the same weight as the earlier beam. We're getting greater depth, greater section modulus, with no sacrifice in terms of additional weight. That beam is going to now be able to span farther and or carry more live load because it has a much higher ability, much higher capacity in bending. What do these look like? This is the sort of standard issue castellated beam. This one, the circles are done with a little kind of fleur-de-lis cut. There's a little bit of wasted material, but as you can see, we have a very, very small amount of material in the web compared with a W shape that would be the same size. This can be part of the aesthetic to the building. It was sort of a standard trope in a high-tech architecture that you would use these kind of castellated beams and express them to show the structural principle at work. And of course, mechanical engineers love castellated beams because there are lots of places to put small ductwork, pipes, things like that, right? The holes around the neutral axis are very, very convenient places for those kind of mechanical things. Now, the other thing we can do is that we can manufacture beams out of very, very small flanges and very, very lightweight webs. And there's not much difference in terms of the mechanics of the beam between a castellated beam and a vector active structure like a truss. In this case, you can see that in the castellated beam, we have a compression flange at the top, and in a truss, we have a compression cord. Right, that top piece is going to be in compression as the load on the deck tries to bend either the beam or the truss. We have a tension flange on the bottom, and in the truss we have a tension cord. This could be a cable in the truss, but usually it's integrated with the deck. And then in the castellated beam, that web, that sliced up web with the now hexagonal holes in it, is going to stabilize the two flanges relative to one another. It's going to take the tendency of for the two of them to slide across one another and shear and resist that. But it's not going to need a lot of material, especially around the neutral axis. And in a truss, instead of a web, we have the diagonal chords. And again, those are fixing the two flanges relative to one another. They're forcing them to work in tandem to reduce the bending load. That's the basic principle behind a truss. We can also, of course, as we did before, zoom out and look at the truss as a series of points or nodes that are held in equilibrium by each of the chords, right? There are multiple ways that we can calculate or interpret a truss. It ends up working a little bit like a beam in this sense, and like a really, really efficient beam, in that the web is replaced by these almost nothing struts, compression and tension struts, that literally hold the two flanges, or in technical terms, the top and bottom chords in place with one another. And we'll see that again and again. Even though we have these four divisions or four types that we think of for structures: form active, section active, vector active, and surface active, we'll see a lot of overlap between them. And we'll often be able to look at a structure and interpret it in sort of one form or another. The more of these ideas that are working together, the more that they're working in sync, usually the more redundant and often the more efficient the structure is going to be. Okay, so that is hacking beams, right? Trying to find ways to make long span beams out of normal beams, usually by trying to reduce the weight, right? Or reducing lazy material. Two basic strategies. One is to do that in the longitudinal direction, look at where the moment diagram is greatest and smallest, and try to tune the beam shape to that, either with a fish belly shape, or, as you saw in the stereoform slab, something a little more complex that mirrors the moment diagram for that situation. Or we can look in cross-section, and we can find ways to look for lazy material in cross-section, usually around the neutral axis, and eliminate it. And in the case of steel beams, we have this very effective, very cost-effective method called Castellation that automatically kind of does that. And that eventually, if we take out enough of the web, we end up with something that's really more of a vector-active structure, a truss, instead of a beam. In the next video, we'll move on and we'll look at section-active structures called folded plates, where what we're doing is we're taking a very, very thin, usually concrete surface, and we're tricking it, making it think that it's actually a much, much deeper surface that we can think of as a beam with section modulus, with compression and tension flanges that we'll look at in some detail.